Welcome. So in this course, we'll learn digital image processing using C++. So some of the processing techniques we'll be learning will include how to convert a colored image to grayscale, how to apply linear contrast, histogram equalization, calculating luminance and linear contrast. Then also learn how to apply filters including Gauss filter, smoothing filter, sharpening, edge detection, Rabat filter, pre-width filter, Sobel filter, and Laplacian convo with erosion. So all these techniques, we will apply them using convolution. So once we learn how to implement convolution, so all these filters will be applied using the kernel or matrix. So also learn how to brighten image, how to apply filter, just like example Instagram filters. So learn how to apply filters on image. So also learn linear contrast saturation and how to scale image by increasing the size or height of the image. So we also learn how to apply arithmetics on image addition, subtraction, and logical operations like and, Nand, or, and so. So we also learn about how to flip image, horizontal flip, vertical flipping, and rotation of image. But the core idea behind this is learning how the image matrix works. So that is the major work which we are going to learn, and the rest will be very easy. So the programming language we'll be using is C++, and we'll be writing everything from scratch without any libraries. So we'll code every processing technique. We'll write the code without including any inbuilt or external libraries. Now, the image matrix, will construct it ourselves. We are going to need a library to open the image and extract the pixels from the image. C++ does not have any inbuilt library that extracts pixels from images. So that is why we'll be using OpenCV in this course. I selected OpenCV because it's the most popular. So, but there are other libraries you can use to extract pixels from images. So we are going to use OpenCV just to extract pixels from images, but we are not going to use it to process the image. But the other courses that use OpenCV to extract the pixel and also process the image, that is different. In our course, we only use OpenCV to extract the pixel, but every other processing technique will write the code from scratch. So this will enable us so that in case you are using any other library, it will be also easy for you. So by replacing the new library with OpenCV, you can still write your code from scratch and everything will work fine. So it's better implementing it this way than using a library to write the codes, which makes the code library dependent, but it's going to look easy, but you won't understand the logic behind it. So that is why we won't be using OpenCV to process the images, only extraction of pixel. So with this, I introduce you to this course, and in our next lecture, we are going to start coding. Any part difficult and want to reach out to me, click on the Q&A and ask your question. So there are different headers here: reviews, learning tools, announcements, notes, overviews. You have to click on Q&A, question and answer. So any question you ask, I'll gladly answer all of them. I've been answering questions before now. So click on question, select course content, ask your question, send it, and I'm going to get back to you. So whatever questions, so long as it's related to the course, I'll answer them for you. Q&A, that's where you're going to select and ask your question. So you type in your question here and publish it. I'm always checking it. I'll see it and get back to you. Thank you. So welcome to our first coding class. Now we have to first of all be able to store the image pixel which we extracted using OpenCV. Now there are different methods you can store the image pixel. You can either store it in a struct, you can store it in a class, you can store it in an array, or you can store it using a pointer, and many other. There are so many different alternatives you can use to store the image pixel. But for the sake of this course, I've chosen to store the pixel within a class. So the name of the class is going to be class image. So this class, we have 1 is going to have a constructor, 2 is going to have its destructor, and then 3 is going to be able to store our pixel within a pointer. So on line 6, we first of all declare the image constructor. Then on line 7, we use the image function to create an image. So to create an image, we call this function on line 7. So it takes as argument 1, the number of rows the image we have, then the number of columns, and finally the depth. I forgot to say earlier that all our image is expressed as a 2-dimensional matrix. So in our next class, I'll show you what I mean by the 2D matrix. So on line 7 is taking as argument the number of rows, the number of columns, and then the depth. So this depth is going to determine whether it's a grayscale image or a colored image. A grayscale image only has one channel or one depth, but a colored image we have 3 channels, which is one for the red, another channel for green, and the third one for blue. That is RGB. So the depth is very important when creating the image. On line 8 is the destructor. So next we need to include some function, because here we will be getting the pixel, manipulating it, setting it. So we need to create function that will enable us to know the pixel at a particular row or column combination. So line 9 and 10 is equivalent to line 11 and 12. So line 9 and 10 is used to get the pixel at a particular location, and line 10 is used to set the pixel at a particular location. So the difference is that on line 10, we have a value which we want to set at that particular location. Then 11 and 12 is equivalent to 9 and 10, but the difference is that get pixel value 3 and set pixel value 3 is used to set for images in a 3 dimension. That is for a colored image. So we've included the depth there on line 11 and 12. So the depth will determine whether we are setting for the red or for the green or for the blue. So if it's 0, if the depth is equivalent to 0, it means the red. If the depth is equivalent to 1, it means green. And if it's equivalent to 2, it means blue. Then on line 13 and 14, we are going to store the rows, the number of rows the image has. On line 14, the number of columns. On line 15, the depth. Remember I told you if the depth is 1, is a grayscale image. That is black and white image. But if it's 3, is a colored image. Then finally, on line 16 and 17 is the actual pointer that points to the image pixel. So line 16 is a two-dimensional pointer. It's going to point for grayscale image, and line 17 is a three-dimensional pointer. It's going to point for colored images. So that is different between 16 and 17. So a complete class will store both the colored image and its black and white version. So that is the function of 16 and 17. So those two pointers, one, the 16 will point to the black and white, that is the grayscale, and line 17 will point to the colored image. So if it is a colored image, we can use the grayscale function to convert it to a black and white image and still store it within the class. So this is all we need for our class. In our next class, we are going to define all these functions. So I will also show you what the image matrix looks like. So depending on your design, it must not follow this particular method, but the compulsory identifiers that you have to be able to store the number of rows and columns the image have. That is what you have on line 13 and 14 and 15, the depth also, so that you'll be able to know if the image is black and white or if it's a colored image. And finally 16 and 17. So from 13 to 17 is compulsory if you need to store images. But 16 and 17 are pointers. So depending on your design, you can decide to use vectors rather than pointers, or you can use arrays also. So but for this course, I'm using pointer, which is what we use on line 16 and 17. The 16 is a two-dimensional pointer, while 17 is three-dimensional for storing colored images. So in our next class, we are going to define all these functions we created. Thank you, and see you in our next class. So in our last class, we learned how to store our image within our class called image. So here, there were list of functions we declared within our class. So here in this file, we are going to start defining them. So you see their contents. So first, on line 1, we've included our image.h header file. Then on line 3, we included the functions.h, which is what we will define next. Though the function.h is just contains list of functions we will be needing and nothing else. So on line 6, we start by defining the constructor. So all our constructor does is to initialize everything to 0 and our pointers to null. So one very common function we'll be using, or one common programming style we'll be using, is to loop through the image matrix. So we use it a lot throughout this course, and I will make out a separate lecture to explain how the image matrix works. So in our next class, I will show you, explain everything about how the image matrix works. Now on line 14, we are going to learn how to create an image. So we use this function, the image function on line 14, to create an image. So after extracting the pixel using OpenCV, so to create our own image, we need three things. We need the total number of rows the image have, and the total number of columns which the image have, and then the depth of the image. So we call our image function. So this is where the class is being created. So on line 15, 16, and 17, we set the rows, columns, and depth, which we saw in our last class, to the value norm rows, norm cols, and end depths. So the norm rows, norm cols, and end depths are the value of the rows and column of the new image we want to create. So we are setting it to the rows, column, and depth. Now on line 18 and 19, we are going to allocate memory to our pointer. So we allocate this memory both for the colored and the grayscale. Reason is that, assuming, which is very often, the images are usually a colored image, but most of the operation will require us to operate on a grayscale image because it's easier. Colored image requires you to operate for each of the channels, red, green, and blue. So we always convert from color to grayscale. So whenever we are creating the image, we are creating for both the colored and the grayscale, even in as much as the image is a colored image. So on line 21, this particular loop will be compulsory. We use it very often throughout this course. So this loop, we are going to use it to loop throughout the image matrix. So for line 21 down to 26, we are allocating memory for the grayscale image, and on line 27, we allocate for the colored image. Now on line 21, to do this, we are going to loop through all the rows of the image, which is what the for loop is doing on line 21. We are looping through all the rows of the image, and we are allocating memory for each of the columns, which is what we are doing on line 22. And for each of the rows, we are looping through all the columns on line 23 and initializing each of the columns in each row to 0. So I hope it's easy to understand. You can ask me a question in the Q&A session and I will explain it more for you. So this is what you will do irrespective of what data structure you are using to store the image matrix. You must allocate memory for it. So the only storage type that does not require allocating memory is a vector. Except you are using a vector, you won't have to go through this stress. So 21 down to 26, we are creating memory. Then on line 27, we are going to repeat the same thing we did on line 21, but here we will be including the depth. So the depth is a 3 channel. So line 27, you can compare line 27 with line 21. So remember, what we are doing is allocating memory for the image. So we added extra parameter on line 31, that is looping through the depth and assigning each of the depth, which is the red, green, and blue, to 0. So next, the image destruct on line 38. So whenever we are done with the image class, we have to delete everything to clear the allocated memory. So which is what we are using the image destructor to do. So what the destructor does is just the way we looped on line 21 and on line 27, we are also going to loop again, but while we are looping, we are now deleting each of the allocated spaces. So on line 39, you can see that we loop through each of the rows, and then we are deleting all the pixels per row. And when we are done, we delete the pointer. Also, remember the difference between the pixel value, which is used to store grayscale, and the pixel value 3, which is used to store the colored version of the image. So this destructor line 38 is just showing us how to delete the allocated memory. So after looping through all the rows and columns, on 39, we deleted for the grayscale image, and on line 42, we are looping and deleting for the colored image. Now, once we are done, on line 47 to 50, we will now set everything to 0. And that is how we implement this destructor. So even if you are using an array as a storage medium, at the end you are expected to free up the space allocated to the array, because the array you are going to use is going to be a dynamic array, because the image pixel sizes will not be fixed. You'll be working with different image sizes. So if you are going to use an array, you are still going to use a dynamic array, and which means you will be able to allocate memory, and you are expected to deallocate the memory after using them. So vector will make this process look much simple. Then on line 56, we are now done with the constructor and destructor. So now on line 56, and this is how to get a pixel. So very often throughout this course, we will be using the getPixel and the setPixel function. So if you want to know the value of the pixel at a particular location, whether it's red or green or blue, we use the getPixel function. So all we need to do is to give the row and the column number, the row number and the column number. The two of them combined will point to a specific location within the matrix, and then we are going to return the pixel value at that row. On line 57, we use the return pixel value at that particular row, and that means you are returning for a grayscale image. Now on line 60, we set pixel. So assuming we want to set the pixel to a particular value, we use the setPixel function. So all you need is the row and the column and the value. So here on line 61, we set the pixel value on line 61. Then, just as line 56 and 60, where we get pixel and set pixel for a grayscale image, we are going to repeat the same for a colored image. Now, for a colored image, which we are doing on line 64, the only difference is that we are going to include the depth. So, because we have to know whether, once we get to the location, we have to know whether you are setting for the green or the red or the blue. So on line 64, we initialize the get pixel value 3, and then on line 68, we are going to initialize the set pixel value 3. So these are the only function which we need. We've described all the functions we called in our image class. So in our next class, we are going to list all the functions, all the signal technique we are going to implement in this course. So if you have any question, please go to the Q&A section of this course and ask your question. And if you're enjoying this course, please, I urge you to give it a 5-star review. It will go a long way to assisting the distribution of this course. So this is all for the image.c++. So now we have two files. The image.h, which is the header file that contains our image class, that is where images are being stored. Now we have the image.c++, which is where we define all our image class function. Then we've included the image.h file on line 1. Then functions.h, we are still going to describe that file. So you see what is contained inside. So for this lesson, I hope you understand about how classes work in C++. So what I've implemented here is the easiest part of classes. So there's no complicated explanations here. But if you see a further explanation, please, you can ask me in the Q&A session of this course. Thank you, and I'll see you in our next class. So welcome. This is what a typical image matrix looks like. It consists of pixels filled up in rows and columns. And the value will usually range from 0 to 255. The reason is because each pixel is made up of 8 bits. So you know 8 bits can only store from 0 to 255. That is 2 raised to the power 8, which is 256. So, but depending on the picture, there are pictures where the pixel can use more than 8 bits. But conventionally, plus most of the pictures I've worked with, they usually range from 0 to 225. That is, you will see like 300 or 400 within each of the pixels. So their range is 0 to 255. 255 is the max because each pixel uses only 8 bits to store the color content. Now, below it, you will see this for loop, this double for loop. We are going to use that particular syntax throughout this course. So I'm using it as an example here. So the first for loop is looping through the rows. So row by row. So, and within each row, another for loop is looping through the column. So very often, whenever we want to operate on each of the matrix, each of the data of the picture, we use this for loop. So you see it very often. So in one rows is the number of rows. So it's going row after row after row from 120, the row on 120 to 249 down to the row from 145. And within each row, the second for loop, which is checking yj is less than the number of columns, is looping within each of the columns of each row. So that is how this matrix works. So now within the for loop, you now see where we said get pixel. So we have to pass two parameters there, the row and the column I and j. So we are going to use this syntax very often within this course. You see I and j. So this is the row and column which is used to mark the position of each of the pixels. So hopefully you understand it. So in our next class, we'll go into the main operations. Welcome. Here we are going to start discussing our main function. So we only included the function.h++, which is where all our code operations is going to be stored. Now, our operation can appear in two forms. The first one is given here. Example, let's take for instance the operation erosion is simply written as erosion and then the file location of the image. So we call them from the command line. So after typing the name of the file, we just write erosion and then the location of the file. So we simply pick the command, we check if the name of the command, and then we apply the operation on the file. Then the second one is for operation that is only applied on two images. You can see how it's written. We write the name of the first image, then followed by the operation, and then the second image, So to do this, we are going to use a struct to store the command line values. So first we have to store 1, the name of the argument, 2, the location of the images, 3, the function to be called. So that is what you are doing in this particular struct on line 8. So on line 5 and 6, we just created a function prototype for a function that takes only one argument, which is one of the image, and line 6, a function that takes 2 arguments, which is 2 of the images. So these are the 2 functions we are going to call. So the prototype is what I created in line 5 and 6. So you can ask me further question if you don't understand how function prototype works. So on line 5 and 6, you can find out that the return type is void. So it means they don't return any argument. And one takes as argument 1 image, and the other one takes as argument 2 images. And the first one is called function call, and the other one is called function call 1. So these are used for the 2 different types of operations. The one that is used for a single image and the one that is operated on 2 images. Now within our struct, the first value we are going to store is called the argument value, which is what type of operation do we want to perform. So this is going to be passed in the command line. So we'll get this value from the command line and store it on line 9 in the string argument value. Then on line 10, print value, we are just going to print, assuming it's erosion, as seen on line 16. So the argument value here on line 16 is erosion. Then the print value is doing image erosion. So we just print to the command line what operation we are performing. We just write doing image erosion. Then line 11 and 12 will depend. One of them will be null because we cannot perform two operations at the same time. So either we set line 11 to null and then we are using line 12, or we set line 12 to null and we are using line 11. So line 11 and 12 will now be the function to call. Assuming it's erosion, here we are going to call erosion and then set the last one to null. Now we've created this struct on line 8. The name is image process. So we are going to create an array of struct. So this array, which is what we are doing on line 15, is going to consist of all the operations we are going to perform that follow a similar pattern. All the operations, including our erosion, calculate contrast, histogram equalization, and all of them. There are too many of them. So all of them is going to be within this image process array. So this is from where we are going to be selecting which particular operation we want to. So now you can compare and see how each of them fits in. So the first one is the argument value. Here the argument values include erosion, calculate contrast, and histogram equalization. Then next to the print value. Here the print value will include 1, doing image erosion, followed by image contrast, doing histogram equalization on image. Then the function call on line 11, whose name is filter. Here we include erosion, calculate contrast, and histogram equalization. Then finally, line 12, which is function call 1 or filters, we'll set it to null because this particular operations require only single image. Now, this is how we are going to repeat it for all of the operations we are going to perform in this our course. Now, this is not a necessary. You can use an if-else statement to write this. So what is simply doing is that we are going to check the command we have in our command line, compare it with all of this to know which command we are dealing with. So here I've filled it up. So by the time we start adding the commands that operate on two images, we are going to see how the null column will move to the third column, and then the name of the function will now go to the fourth column. So this is much faster or probably more advanced. So in case you are finding it hard, another simple method to express this is just to use a very long list of if-else block. So where you are using if-else or a switch statement to compare the argument we have in our command line. So you can now be checking if the argument is equal to erosion, if it's equal to calculate contrast, if it's equal to histogram equalization. If they are equal, you print the second column. Then after printing the second column, you call the function on the third column. So this third column are a list of functions we are going to call depending on what operation we are performing. Already we've defined the function prototype. I told you they all return void. That is, they do not return any value. And they take as argument the image, a single image. So now on line 32, we've successfully added all the operations that require just a single image. So including the luminance, L rotate, left rotate, right rotate, vertical flip, horizontal flip, edge detect, sharpen, operation, convolution, and so many of them which we can't view from here. So next, now on line 33, we are now going to start adding the operation that requires multiple images. So the major difference between them is that they are going to call different functions. So instead of writing the functions under the place where I write normal function, we are going to write it at the end. And then the null value will now be where the function names used to be before for the first type. Now, as you can see on line 34, where the initial function for the single image operations are, we are now assigning null to it because we won't be calling that particular function. Now, where the single image function is writing null, that is where we are going to call our function that operates on two images. So this is the main difference between the first part, which is the part that operates on a single image, and the second part, that is the part that operates on multiple images or two images. So I've minimized it so you can see. Now I've started writing the names of their functions. So this is the list of all the functions. The upper parts are the ones that take as argument single image. The lower part is the ones that take as argument two images. So these are the two parts we are going to include within our image process array. So whenever we want to perform an operation, we are going to loop through this array and check which particular operation we want to operate on. You see how we do the comparison and the selection of function. Bear in mind that there are other functions that do not follow this particular convention. So those ones, we are just going to write them out as an if-else statement. So thank you. See you in our next class. So in our next class, we are going to implement, and then you see how we loop through this array and select a particular function we want to operate on. Thank you. Welcome. So in our last lesson, we listed all the image operations we are going to need in this array called list, which is of the struct image process. So you can see where the first column is the command line arguments. So the second column is what we are just going to print before starting the operation. Then the third column is the actual function that is going to be called, and the fourth column is also function. So the third column is for function that takes only one argument, which is the image, and the fourth column is for functions that take two arguments, that is two images. So here, everything here, all the operations here take only one argument. That is, one operates on only a single image. So that is why the third column is where we list the function, and then the fourth column is set to null. Then, but if they are taking more than one argument, that is for image operations on two images. Example, here you have the AND, the NAND, the OR, the XOR, add, and the rest. So you can find out that here, is where the functions will be, and then we've set this other one to null. So that is the major difference. So next we just declare this print help function. So this function is if you enter an invalid command, so we are going to call this printf function by default. That is, after we've looped and we were not able to match the operation. That is, if the operation you entered is not on the list, we are just going to simply call this printf function. So you just tell you press this button and how to get the correct code. So next, now we are going to define our main function. So our main function, we are going to read the argument count and the argument values, because these operations will be called from the command line. So first is now going to check the number of arguments we have. Now, for operations that require single image, the argument count is usually equivalent to 3. The first argument will be the executable file. The second one will now be the operation, maybe if it's erosion or filtering. Then the third argument is equivalent to the file location the image we want to apply the effect on. So if the argument is equivalent to 3, as we check on line 55, then is most definitely a single image operation. So what we are going to do now on line 56, we create an image class. I'm still going to correct line 56. So here you can see that from 16 to 32, there are 17 operations. So on line 56, we are going to call the read image function. So this function read image, we are going to describe it in our next class. So what it does is it reads the image and produces the pixel values. And this is the only function that requires the OpenCV, because in this function is where we are going to use OpenCV to read the pixel. And now argument value 2 is equivalent to the file location. Remember, argument value 1 is the operation. Argument value 0 is the executable file. So 2 is the name of the file. So we read it using the read image function. On line 56, image in is of type image class. Remember, we created image class in our previous lesson. So on line 56, I'm still going to write image in. So what we are going to now do on line 58 is that we are going to loop throughout the list. This is our array list. So now we start from count, when count is 0 till when count is 17. For operations that have single value, that take single image, there are total 17 of them. So we are going to loop from 0 to 17. Now on line 56, I've added the type image, remember. So on line 58, we now loop through the list. So what we are checking is we are comparing argument 1, argument value 1, which is equivalent to the operation we want to perform. And we are comparing it to the array list of the argument value, which is the first row. So then we are looping using the count. So if a match is found, what we are going to do on line 60, we print the second column. Remember, the print value column is what we print on line 60. If there is a match, then on line 61, we now call the filter function and pass the image, which we read on line 56 as an argument, which is what we are now on line 61. So we pass the image in as arguments to the filter function. So now remember that the count is used as an index to select the particular one we are on. So outside the if block, we increment count plus plus. So that is how we are looping. Now on line 66, if the argument value is 4, that means the argument 0 is the executable file, argument 1 is the first image, argument 2 is the operation, and argument 3 is the second image. So that means it involves an operation of 2 images. Now remember, the operation of 2 images is now going to start from line 18 down to the end. Already, the operations that take single image started from 0 to 17 in our array. So now we are now going to count from 17 down to 24. Here you can see it's on line 34 to 39. So these are the only parts we are going to check for multiple image operation. So 34 to 39 is the only list we are going to compare. So we won't start checking all of them again. So once the argument is up to 4, we now check from 17 down to 24. So already on line 67 and 68, we call the read image to read the 2 images. So we name the first one imaging 1 and the second one imaging 2. Then on line 71 is where we start looping. We loop through the list, starting from 17 up to 23. Since the loop says when count is less than or equal to 24. So we are checking from count equal to 17 up to count equal to 23. Now on line 71, the argument value 2, we check argument value 2 in our command line is equivalent to the operation, the image operation. So we compare it with the one in the list. If there is a match on line 72, is where we print the print value column. So on line 73, we call the filters function. I'm passing both images, imaging 1 and imaging 2 on line 73. So this is how we call the function. So the major achievement here is line 73 and line 61, which is where we call the image function. That is the major accomplishment here is line 61 and line 73, where the functions were called the filter, which takes single arguments, and the filters that take 2 images. So next, there are other operations that do not follow this convention. That is, probably they require more than 2 images, or maybe they don't require an image at all, or probably they require an image and another argument which is not an image. So that is the last part which we are going to add on this line 78. Now, what we've done is not compulsory how to do it. You can use a very long if-else statement to place them. So instead of building this array block or whatever, you can just write a very long if-else statement where you are comparing what was added in the command line to the list of operations you have. So you can be checking if what you have in your command line is equal to this. If it's not equal, you go to the next if statement. You keep checking. So it's going to be a very long if-else statement, but it's still going to work. So if this particular procedure looks complicated, so in our next lesson, we are going to complete the remaining part of our operations. So if you have any question, please go to the Q&A session and ask them, and I'm going to answer them for you. Thank you. So welcome. In our last lesson, we've already started writing how to call our functions, the ones which take as argument a single image and one that operates on two images. So here they are the rest, which does not follow any particular order, mostly because they take extra parameters. Example, probably if you want to increase the brightness, so you have to add also to which extent, whether you are increasing it or you are lowering it, and what level you want to increase it or lower it to. So these extra arguments which you are going to add to the command line is going to affect it. So that is why I place them in a separate else block. So, but one thing common among them is that the argument value 2 must contain an image which they are going to operate on. So since they are also image operation functions, so on line 79, so all of them will have an image in the argument value 2. Then they include on line 81 the linear contrast saturation. So we use the string compare argument to compare argument value 1 and the linear contrast saturation. So if they are equal, then this particular operation will take more arguments. So all you need to do at this particular point is just to see how the operation is being called, because in our future lesson, when we start discussing each of them, we are still going to come back here and show you starting from the scratch when we compared it with the argument value. So example, this linear contrast saturation requires a minimum and maximum value which you want to saturate the contrast. So these two values now you pass it as argument 3 and argument 4 on line 82 and 83. So then by on line 84, when we now call the linear contrast saturation function, you can see that it has two extra arguments, S-min and S-max, and none of them are images. So the functions I'm writing here do not follow the convention of the ones that we added in an array above. So on line 87, aside from the image, we are also going to take as argument the level we want to brighten the image. Then on line 90, we are going to compare again another function. Filtering. Yes, in example, if you are on Instagram, you see how the Instagram filter works. That is exactly what we are going to implement here. So it will take extra arguments, how much you want to filter the red, how much you want to filter the green, and how much you want to filter the blue. And then, of course, the image you want to apply the filter to. So line 96, we check again for multiplication, and then finally you also check for scaling, how to scale images. So here we are just checking out multiplying an image. So on line 100, we check scaling. We'll be able to scale image probably by increasing the width or increasing the height of the image. So for the scaling, we check for the length and the width. What factor are we using to scale? Are we reducing or are we increasing? and by what value. So this is what we do for the scaling. So now at this point, we have called all the image operation function. So by our next class, we are going to start defining them one after the other. So on line 109, if we couldn't locate any of your operation, we simply call the printhelp function, and that is all. So in our next class, we are going to start defining all these functions that we have created. Thank you, and see you in our next class. Welcome. Before we go further, in our next class, we are supposed to start using OpenCV. So now you need to first of all do the OpenCV installation. So in the attached course file, there is a video added there. So you need to watch that separate video. It's going to teach you how to install OpenCV in Microsoft Visual Studio. So you must watch it. The installation process is very rigorous and tedious. But if you follow the video carefully, step by step, you'll be able to install it properly. Like I told you earlier, we only need OpenCV to be able to read the image pixel. C++ does not have any inbuilt library that will enable you to read image pixels. So you need an external library. Though there are so many other external libraries you can use. So the beautiful thing about this course is that it's not just OpenCV you can use. You can use any C++ library that is easy for you to implement. So once you're able to read out the image pixel, that is all you need. The rest of the manipulation will be done by ourselves from scratch. So watch the video and install OpenCV on your PC. If you don't want to use OpenCV, you can use any other library of your choice. But all you need to be able to do is to get all the image pixels. So thank you. In our next class, I will assume that you've installed OpenCV. Then we'll start reading the image pixel. Thank you. Welcome. So at the beginning of this lecture, I will assume that you've installed OpenCV as we discussed in our last class. So here, this is where the real implementation starts. So we included some libraries, and then on line 5, I've included the OpenCV header library, and on line 4, I've included our image class. Then on 8, we have a vector. We will be using vector. Instead of using dynamic arrays, vectors are preferable, and you'll see where we use them. Then on line 9, we've included functions.h. Functions.h is just a header file where we declared all our image operations. So it's just like a header file that links the main class with this function.hpp. So the first operation we are going to implement is how to read the image pixel. How to read the image pixel and how to write the image pixel are the only functions we are going to implement using OpenCV. Because just like I told you earlier, C++ does not implement it. So if you know any other library you've used in the past to read pixel or to manipulate pixel, you can implement it rather than using OpenCV here. Now, but for OpenCV, we are going to use it for the read image and also to display image. So on line 11, we've called the read image function. Now, you can see that the read image function returns image, a type of our image class. So that is why in our main.c++, whenever we read the image, we return an image. So you can see that on line 11 is returning an image. And also, it takes as an argument the location of the file, that is the fname. So remember, in our main.c++, we simply use the argument value, which is the file location, as the argument. So here is the fname. So to read an image on line 12 is how OpenCV reads an image. So you just write in read, you write the location of the image, and you read it into a type mat, M-A-T. So the type is mat on line 12. So the name of this mat is called image. It's different from our image class. Our image class starts with a capital I, but this mat on line 12, the image starts with a small I. So we just check if it's successfully read. By on line 13, we do if image.empty. So we say file not found. But if it's found, then on line 17 is where we create our own image. That is, the image we create on line 17 is where we are going to copy we are going to copy the image on line 12 into the image on line 17. You know that the image on line 12 is OpenCV image, is of type mat on line 12. So we are going to copy it into our own image type on line 17. So which is the one we are going to be able to use in this class. So we use the image class on line 17. So it takes as arguments the rows, the column, and the depth. So the depth here is channel. So in OpenCV, to get the rows and columns or channels of an image, you write the name of the image dot rows, or the name of the image dot cols, or the name of the image dot channel will return whether is a colored or a grayscale. If it's colored, the image dot channel will return 3 for R, G, and B. But if it's a grayscale image, it's going to return 1. So that is what we did on line 17. So we just created our own image, and it's going to, the number of rows, column, and depth is equivalent to the number of rows, column, and depth of the image on line 12. So you can see how we did it here on line 17. So this line 17 is one of the functions we used in our image.h header file. So next, on line 19 and 20, remember about the for loop I told you. So all it does is to loop through the image matrix, row and column. So while the for loop on line 19 is looping row by row, the loop on line 20 is now for each row, we are going to loop again for each column. So this is how we'll be able to loop through every individual pixels. So that is what the two for loop on line 19 and 20 is doing. So for a colored image, this is how we get the value of the pixel on line 21. So in OpenCV, the pixels for a colored image is of type vect3b. So here we declare the vect3b, and we use one whose name is intensity. So it's equivalent to the pixel at each particular column. So that is why we've done image.at-vect3b I, j. So this is the syntax of getting the pixel in OpenCV. You use image.at, the location I and j. So I and j stores the row and column of that particular image you want to get the pixel. Now, after getting the pixel now, we are now going to use our own set pixel value 3 function to set the pixel for our new image. So on line 21, we copy from OpenCV. Then on line 22, 23, and 24, we are going to store it into our own. So, and this is how we do it. So remember when we discussed the set pixel value 3 function. So it's going to take as argument the row, the column, the depth, and the value. So here the column is I, then J, then the intensity. So that is what we are doing on line 22, 23, and 24. We are now copying the intensity from the image on line 12, and we are now copying it into the image on line 17, which is the one we created. So ask me a question if you don't understand this place. So I repeat again. We copy the pixel value on line 21. We are copying from the image on line 12, which is the image OpenCV read, and we are copying into line 22, 23, and 24. That is img.setPixel, which is the one we created on line 17. So the image on line 12 is image, while the one on line 17 is img. So that is the difference between these two images, their name. So once we are done, we can decide to display the image. So use the imshow. Though it's not necessary. So I just decided that after reading the image, I display it using the imshow. On OpenCV has the keyword imshow. Then on line 28, we use the wait key. So this wait key means that once you see the image, you press any key, it will disappear. Then on line 29, okay, on line 31, we now return the new image we created on line 17. Then on line 30, I will just display the number of channels. It's not really necessary. Then on line 29, I'm going to convert the image to grayscale. So I call the grayscale function and pass the image to it. So we are going to see how we convert image from colored to grayscale next. So if you have any question, please kindly let me know in the Q&A section of this course, and I will be very willing to explain it to you. So next we are going to discuss line 29, the grayscale. So it's very important to have both copies, the grayscale and the colored copy. So the one we have already is a colored copy, because you can see that on line 22, 23, and 24, we are using set pixel value 3. So we are storing the colored copy. So you will also see that we are setting 0, 1, 2 is for red, green, and blue. So but on line 29, we are still going to set the pixel for the grayscale. So next, that's what we are going to discuss next. Thank you. Hope you understand this. Ask me a question in the Q&A session, and I will answer it instantly. So thank you, and see you in our next class. Welcome. So in our last lesson, we learned how to read an image pixel, to get pixels out of an image using OpenCV library. So I told you can implement any library of your choice also. So here in this lesson, we are going to learn how to convert a colored image to grayscale. So one benefit of that is because, grayscale is a single channel. So it's easier to work with compared to a colored image that has 3 different channels. So, but most of the application we do with grayscale can likewise be performed using a colored image, but it's faster because it's a single channel. So how do we convert a colored image to grayscale? Now it's simple, we just combine the red, the green and the blue together to get the grayscale. But there is a calculation behind it. There is a formula for it. So you won't calculate the whole red, green and blue together. If you add them together, you are still going to get a grayscale, but a darker shade. A shade that will be very dark, close to black or so. So, but to do that, you use this particular formula here. So you add 0.3 of the red plus 0.59 of the green plus 0.11 of the blue together. So in essence, you are not going to add them the full value together, just a percentage of them. So it's assumed that a percentage of the three colors make up the grayscale, not the whole color. So that is what we are going to do in this class. So as you can see, we've declared the grayscale, and now it's returning type image, but I will later change it to void. It does not return any type. It simply converts the image to grayscale, and that is all. So on line 11, it's supposed to be void grayscale, not image grayscale. Now remember the two for loops on line 14 and 15. I told you throughout this course, we are going to use this particular for loop. Is the key. So this for loop simply gives us access to all the pixels within an image. So for whatever pixel we get, we manipulate that pixel and get a new value for it. So line 12, we check if the depth is straight. That is, we have to make sure it's a colored image first before converting to grayscale. So now on line 16, we now have access to every single pixel within the image. That is on line 16. So remember on line 14, we loop through the rows. So within each row, on line 15, we are looping through each column. So this is how we get access to all the individual pixels. So by adding I and j, we can effectively get the particular pixel in the loop. Now, we are going to do the calculation and store it in the integer called val on line 16. So as you can see already, we started multiplying them. So on line 16, we've done 0.3 times image.getPixelValue3. So when you remember that getPixelVal is for single channel or grayscale, but whenever you add 3 to it, as we describe in our function, it means for colored. So and the color here is 0, ij 0, so and 0 is red. So we now do 0.3 of red. On line 17, we now do 0.59 of green. And then on line 18, we will now also do 0.11 of blue. So we add them together into the integer called val on line 16. So what I'm casting them to double. The getPixelValue3 returns an integer. So, but I'm casting it to double so that I'll be able to multiply them with all these decimal values, 0.3, 0.59, and 0.11. So after multiplication, the new value will now be stored on line 16 as val. So we now call the setPixelValue next. So after the calculation has doubled, we cast it back to integer on line 16 before storing it in the val. So now remember, we are using getPixelValue3. So this getPixelValue3 is getting the pixel value of a colored image. So we will now call the setPixelValue. We are not going to call setPixelValue3. We are calling simply the setPixelValue. So on line 21 is now setting for a grayscale image. So it's very important to note the difference. So we now call the setPixelValue and add the new generated value to it. So when the for loop is complete, line 21, I've set the grayscale pixel value for all of the new grayscale image. So we'll do testing very soon. We are going to test everything we've been implementing in this course. So thank you, and I will meet you in our next class. Welcome. So in our last lesson, we saw how to convert a colored image to grayscale. So here we are going to write a function to display the image. So the function will be one will be able to display a grayscale image, while another function will display the colored image. So to do this, remember that what our image class is the class stores arrays of pixels, but not an image. So to display an image, we have to convert those arrays of pixels in our class back to an OpenCV image. Remember, it's only the external library that can read or write an image. So there is no inbuilt library for it. So to do this, all we need to do is to pass our image class as an argument to the display gray on line 50. That is, if we want to display a gray image. So what we do next is to create an OpenCV image, just an empty one. So if we are able to create an OpenCV image, an empty one, then we can push all our pixels into that OpenCV image. So an empty OpenCV image is now created on line 51. So this is the syntax for creating an image, and this one is empty. Then the first two arguments are the rows and column is going to have. So the rows and column on line 51 will be equivalent to the rows and column of our image we want to display. So in our case, the image is img, but here I've written image out.rows. It is actually an error. It's supposed to be img.rows and img.cols. Then followed by CV 8. 8 means 8 bits is used to store the pixel. And then the C1 means how many channels? 1 channel. So assuming is a colored image, is going to be C3. That is 3 channels. So but here is C1, meaning it's just a grayscale image we want to display. And the 8 there represents that each pixel can be stored with 8 bits. That is 2 raised to power 8. The maximum value the pixel can have is 255. Then scalar 000, that will be the background. So everything, so what we've done is a pure black, empty black image here. So this line 51 is more like a placeholder. Then after that, we now start putting our original data there. So the scalar 000, you can give a background image of your choice there. But so long as you don't cover it with pixel, it's going to remain black. But in our case, we are going to fill the whole space with pixels. So at the end of the day, the background won't be black. So on line 52 and 53, remember the for loop we used to loop throughout the image pixel. So while we are looping, we are now copying the pixel from our image class into the OpenCV image. So we are doing this on line 54. That is what we are now doing. We are copying all our pixels from our image class into the OpenCV image on line 54. So the name of the image we've created is img, capital G. And the name of, so you've seen on line 51, I've corrected it. It's no longer image out. It's now image.rows and image.cols. So on line 54, you can now see that our image class is img, while the OpenCV image is img with capital G. So observe what you are doing on line 54, how we are copying from our image class to the OpenCV image. So when we are done, the OpenCV image contains our original picture. So on line 57, we can just display some output to the command line indicating the number of rows and columns. Then on line 58, we use the imWrite object to store the image. So there are two functions we are using here, imWrite and imShow. So imWrite, you use imWrite when you want to store the image, and then you use imShow when you want to display the image. So these two functions are OpenCV function. So they are going to help us to display the image. And then on line 60, the wait key 0 means that if you press any key, the window will close. So this is it about how to display a grayscale image. I'll also show you how to display a colored image. Then we run an example. So to display a colored image, we use this function display RGB. So I'll simply copy everything in the display gray function into this new function and make little changes. So you observe carefully to see the difference between how to display a colored image and how to display a grayscale image. So as you can see, I've copied the code from the display gray into the display RGB function. So now watch the changes I'm making. So now instead of copying the pixel, we are going to copy both for the red, the green, and the blue all together. Now watch how we are doing it on line 67. Now remember in our previous when we were displaying gray, you found out that this particular line dot value 0 was not included because this is now a vector which contains other items inside it. So we are now referencing those items with this index dot value 0, dot value 1, dot value 2. And also we are now using get pixel value 3. It's no longer get pixel value. Now get pixel value 3, and we are now writing the full index up to the channel. So you can now see ij0, ij1, ij2. So this is how we are going to copy for colored image. And then finally on line 64, we change the channel to 3. So it's no longer C1, it's now C3. So this is simply how we display for colored image. So the process is similar for both. So in our next class, since we now have this function to display image, we will try an example and show you how the image is being displayed. Hopefully your OpenCV installation was successful. If not, please kindly let me know. Thank you. So now we are ready to test our program. So first of all, I assume that your OpenCV installation was successful. If not, please check our previous video where I attached a tutorial on how to install OpenCV. Then next, it's time to test our code to see the picture. So first thing, we have to, all these functions here, all these functions we called here, from erosions down to luminance and the logic and down to addition. Also, these other ones in between, like the linear contrast, brightness, filtering, we are going to go to the functions.h file and declare all of them. So that is what I've done here in the functions.h file. I've declared every single one of them here. Because if you don't declare them, the compiler will throw an error because it doesn't know where to find those functions. So after declaring them here, I'm trying to initialize them here. So this is how I did it. So nothing yet has been done. This is the functions.h++. Now I'm actually typing with my Visual Studio Code, but I'll be doing the testing on Visual Studio because Visual Studio is where the OpenCV was installed, but VS Code is faster to use. Visual Studio usually hangs. So that is why I type in VS Code and I test it in Visual Studio. So for the display, remember, once we read the image, down here we call the grayscale. So when we call the grayscale, let's go to the grayscale. The grayscale converts it to a grayscale image. So next, I call the display to display them. Though after this testing, I'm going to delete them because we are not meant to display after converting to grayscale. But just for testing purposes, I've called the display gray and display RGB for them. So that after converting to grayscale, we'll be able to display both the colored and then the black and white or grayscale. Then again, within the display RGB, remember I told you that what does the display is in show, and in write we store the image at the given location. So you can put a location you want here, and then in write we store the image for you there. Now it's time to go over to my Visual Studio for the testing. Now I'm within my Visual Studio. When you've done everything you have to do, remember to call this function, we go to the command line. So I'll navigate to the command line by I click on the project. I have to go down to properties. So I'm assuming you already know how to use Visual Studio Code, that I won't be teaching it in this course. But what I'm trying to do is that I want to go to the command line and add the arguments. So you can actually check it on Google or YouTube how to add command line arguments in Visual Studio Code. But this is just a simple method. You go to properties of the project you are working on. You click on debugging. So here on command argument, you can see I've called erosion. So this is my command line argument here, erosion, and then the location of the picture. Erosion and then the location of the picture is cc.jpg. So if I open this cc.jpg here, this is what the image looks like. So it's simply an image of a cat. So this is the image we are going to use for our implementation here. So we are going to convert this image to grayscale and display it also. Then, so you've seen that my command line argument is okay. So I will simply click on local window debugger. I assume you can already use this, but you can use other IDE of your choice. But the most important is to have your OpenCV installed properly on it. So, example, if you're using Mac, you can use IDE of your choice, so long as you're able to install OpenCV on it. So the only reason I'm using Visual Studio is because that is where the OpenCV was installed. I wasn't able to install it on VS Code. So now the image has been displayed. I'll close it. Now this is the grayscale image here. You can see it has converted it to grayscale. Then this is the RGB here. So, and remember here I've shown the columns and rows. Now nothing is going to happen because all we've done is just to do the display, because the erosion itself is still empty. I've not included anything to it. So we'll just simply display the image until it's time to call the function. So now we are done. I'll delete this thing back. So we've tested our first code and it's working properly fine. So in our next lesson, we are going to start testing other image operations. So thank you so much, and I'll see you in our next class. Don't forget to send your question in the Q&A session of this course. And leave good likes. Thank you. Welcome. So in this lesson, we are going to start with horizontal flipping, how to flip images horizontally. So example, you can see the picture of this cat. So if you flip it, the right side goes to the left and the left side goes to the right. So consider this image matrix here. So where the rows are represented as I and the columns are represented with J. So these are the columns, column 0, 1, 2, 3, and 4. They are the J, while the I, which are the rows, are 0, 1, and 2. Now to flip it, we have to move the left to the right and the right to the left. That is, we have to swap the columns without swapping the rows. So this is the formula we are going to use to do it. So the formula here, the I remains the same because the I is the rows and they are unchanged. So the columns, to change the columns, we do cols minus J minus 1, where cols represent the total number of columns and the J represent the particular column we are on. So if we apply this formula to this image matrix, we are going to get this. So this is the new transformed image matrix. So you can see that the left column have moved to the right and the right have moved to the left. So we are going to implement this formula in our lesson, in the coding lesson next. Now for the vertical flipping example, to flip this cat image vertically this way. So we are going to use a formula very similar to the other one, but as you can see now, we are flipping the rows and not the columns. So the column, which is J, will still remain the same. But the rows, which is I, will now use this formula to represent it. Rows minus I minus 1, where rows is equivalent to the total number of rows. So when we apply it to this matrix, we get this. So now this is the new image matrix. So you can now see that here all the columns remain the same, but the rows have been flipped. So this is how we are going to implement it in our next, in our coding lesson. So next is how to rotate to the left and then to the right. So consider this cat image again. Let us first learn how to rotate to the right. So when we rotate it to the right, you can now see that using this particular formula here, this is the formula we're going to use to do the rotation to the right. So if you rotate it to the right, you can see that what we did here is that we've swapped the I and J. So, and not only that we swapped the I and J, we also flipped the J after the swapping. So without talking much, let's implement it here. So if you implement it here, this is the new matrix we are going to get here. Then next, for the left rotate, so consider the cat image again. So here is still equivalent to the right rotate. That is, we are going to swap the I and the J. But after swapping the I and the J, we still have to flip the I. That is flipping the rows. So that is what it means to rotate. So this is the new image matrix we are going to get. So in our next lesson, we are going to implement it and then we also test it. So thank you and see you in our next class. So now let us implement the horizontal flip and the vertical flip in our code. So I've gone to where it was declared. So first, when we are flipping, we won't flip within the same image. So we have to create a new image. So that the flipped image the flipped pixel will now be in the new image, not in our original image. So this is how we are creating the new image on line 100. So we call our image class, then the name of the new image is called new image. So we call this image function and the image we have exactly the same rows and column as the original image which we've passed as an argument here. You can see here we've passed the IM, the name of our old image IM. So next on line 101, we are going to call the two for loops. So within the for loop is where we are going to implement the formula I showed you in the previous example, where we do the column minus J minus 1. So you now see that the new image pixel will be equivalent to the transformation of the old image. So here on line 103, we are setting the pixel values. So now remember the syntax: pixel value 3. On line 103, we set pixel value ij, the depth 0 since it's a colored image. Then instead of putting a value, instead of putting a value to set, we are now going to get the value in the old image and then we transform it using the formula in cos minus j minus 1. So that is how it works. Now, since it's colored, we are going to perform it for the 3 channels, for the red, the yellow, and the green. So you can see I'm changing the index 0, 1, 2, the same to the one where we got the pixel. So it's as simple as this. So you can see that the old image has been transformed using the formula co minus j minus 1, and we assign it as the value using the set pixel value on line 103, 104, 105. So that is how we perform horizontal flip. So the same way we will do it for the vertical flip. But remember, the vertical flip has a little change in it also. So we copy the same formula and paste it in the vertical flip. So within the vertical flip, we are going to do some little changes also. So watch, just the same. Now in the vertical flip, all the J which is the column will still remain. We are only going to manipulate the rows. So we now do the rows minus I minus 1. So here we are transforming the old rows by doing rows minus I minus 1 and assigning it to the new rows here. So this is how we implement the horizontal and the vertical flip. So by the time in our next lesson, we are going to simulate it and then you are going to see the change. So thank you and I'll see you in our next class. So now we are going to test them, the horizontal and the vertical flip, which we just did. So I'll go over to Microsoft Visual Studio. Then I need to set the command line parameters. So here you can see that is in each flip, that is a horizontal flip. So I'll now run it. So now this is the original picture. This is the first picture. Remember from our code, we will first display the original picture. Then when I close it, you will now see it flipped horizontally. So you can see that's a swapped. So I will also test for the vertical flip. So I will change the command line argument to v flip. Then I'll try it again. So it has already flipped. So the first image here has flipped. The flipped image. This is the flipped image. So if I close it, it's displaying the black and white color. So I think it's a mistake. I'll have to change it. Okay, yes, this is it. So you know we are dealing with the color, not the gray. So I'll now change it back to color. Then I'm supposed to display the original image, which is the IM, and then the new image. So this is it. We are going to test it again. So as you can see, this is the original image. When I close it, it has flipped vertically. So this is a simple way of implementing a vertical and horizontal flip. So in our next class, we are going to try out the left rotate and the right rotate. That is rotating 90 degrees to the right and or 90 degrees to the left, which is clockwise and anti-clockwise. So that is it. In our next class, we'll discuss the left and right rotations. So see you, thank you, and I'll meet you in our next class. So welcome. In this lesson, we are going to implement what we discussed in our last class about the right rotation and the left rotation. So just like I told you, if you are rotating into a new image. So the first thing we are going to do is to create a new image class. So we call it the new image. So we will use it throughout this course. So for every transformation we do to an image, we first of all create a new image where we are going to apply the transform to. Now, the new image will have the number of columns, the number of rows, and the depth of the old image. So after that, we need to apply the transformation to all the pixels. So we use the double for loop. That is the first for loop loops through the rows, then the second one will loop through the columns. Now we are now setting the pixel for the new image. So we are going to implement that our formula. So remember, we are going to swap the I and the J. So instead of ij, j will come first, then I will now come last instead of the other way around. Then also we are inverting the j, so we now do equals minus j minus 1. So the new value will now be the original value from the original pixel. So that is why we are now doing im.getPixelValue3. So you can see we are getting the original pixel by writing ij. So the original one, we are not transforming anything in it. So we just obtain the original value, then we do the transform to it. So this is simply how we do the right rotation. So once we are done, we are going to display the new picture by calling our display class. So display the old image and also the new image we created. So for the left rotate, we just copied exactly the same from the right rotate and paste it here, but you can watch how we are doing the difference between them. So normally we are still going to swap the I and the J also here, but the flipping will now be on I. Unlike in our previous lesson, it was on J. So here we now do the flipping on the I. So that is it. Then in our next class, we are going to simulate it. Okay, let's do the simulation here already. So now we change this from V flip to L rotate. Now this is the original image, When I close it, it has flipped to the left. So let's change it from the left rotate to the right rotate and test it again. So this is the original image. It has now flipped to the right. So this is how the left and the right rotation, or clockwise and anti-clockwise rotation, works. So in our next class, we'll treat another transformation technique. Please, if you like this course, consider giving it a 5-star and a nice review. Thank you so much. Welcome again. So in this lesson, we are going to talk about Otsu Binarization. So what is binarization and what is the uses? So binarization is used to spread the colors of a picture into only two colors, white and black. Now, when I mean white and black, I do not mean grayscale. No, in grayscale, the colors range from pitch black to very light color. If it's a number of pixels, you will say from 0 to 255, single channel. So now, but in grayscale, you can have different colors like light black, very dark black, brown color, gray color, a very little shade of white, very extreme light shades. So different shades of white and black is contained in a grayscale. But in a binarized color, so just only two, white and black. So we are going to implement it later. And we see how very useful binarization is. Now, for you to grade a color picture or a grayscale picture into only two colors, white and black, you need what we call a threshold. A threshold is like a benchmark, maybe a particular level that demarcates the white from the black. So maybe you have a color picture where some part is red, some are blue, some are light green, and so on. So you need a particular threshold where you can say any color below this particular threshold is going to be black, and every other color above it is going to be white. So that is what a threshold does. So once you're able to pick a particular threshold, you can be able to divide the colors into white and black. Now, selecting the threshold manually is easy. You can pick any number and then you use. But in digital image processing, the threshold has to be selected automatically based on the picture, because different pictures have different threshold. You can't implement the same threshold for two pictures. So you have to be able to find the center of the colors where you can divide them into two equal parts. So, and one way of finding the threshold of each picture individually automatically without having to do it manually yourself is a binarization method called Otsu Binarization. So this method was invented by a man named Otsu. There's his full name. Then I will give a link on Wikipedia that went in depth about it. But for the sake of this course, I will simply explain what Otsu Binarization is and give you examples on it. So next, let's talk about histogram, image histogram. Now consider this image pixels here. Now by the side, you have this histogram. So this histogram shows the distribution of the colors, that is the frequency of each color, how frequent each color appeared. Now, this image histogram is very useful and very important in image processing, and we are going to implement it for Otsu Binarization. Now, what we mean by binarization? Now, considering the histogram, we have to pick a threshold where we can say below it is black, above it is white. So in this histogram, assuming we pick 2 as a threshold, that means all places that has red, which is 0, and yellow, which is 1, is now going to be black, and all the places that has green, which is 3, and orange, which is 4, is now going to be white. So we can now include 2 to be black too, that is the blue ones. So this is what we mean by binarization, picking a thresholding. So you can pick another number, assuming now we are picking manually, then we can pick 3 as the threshold. That means all the red, yellow and blue is going to be black, and only the orange color will be white. Then again, if we pick yellow as the threshold, that means red and yellow will be black, while blue, green and orange will be white. So that is what we mean by manually picking a threshold. But Otsu is going to pick his own threshold by calculation. So it will automatically find the best number. So in this our chart now, it can either be 0, it can either be 1, it can either be 2, 3 or 4. So it's going to pick the best threshold for us so that the picture will be distributed properly. Because assuming you pick red as a threshold, that means only red will be black, every other thing will be white. So the picture won't be binarized properly. So Otsu does a calculation to be able to choose the perfect threshold. So, and that is what we are going to discuss next. Now, this picture here clearly differentiates between a grayscale image and a binarized image. So, as you can see, the first column are all grayscale images. The second column are binarized images, and the last one is the image histogram. So you have now seen that in a grayscale image, they have different shades of white and black. But in a binarized image, there's just only 2 colors, white and black. So in the histogram, you can see where the thresholds were set. Now, for Otsu to pick threshold for us, it calculates variance. Now, let's take an example. Consider this image matrix, and this is the histogram distribution. And we pick 3, for example, as our threshold. That is manually, we select 3. So here now, you can now find that from 2 down, we refer it as the background or the black side, and then from 3 to 5 we refer it as the foreground or the white side. Now let us calculate the class variance. So this is the formula for calculating it. So first of all, get their weight. So you can see that the background part consists of 0, 1, 2, and their frequencies are 8. The frequencies are 8, 7, and 2. So, but for the foreground, there are 9, 6, 6, 9, and 4. So now the total of both of them is 36. So we add them together and divide them by 36. It's more like finding their separate averages. So Then to calculate the mean, we multiply each of them by the original value. Here the 8 is for 0, the 7 is for 1, the 2 is for 2. So we now calculate the mean using that same formula. Now while we are calculating the mean, we are using just the sum of each of them, not both of them. So the 17 is equivalent to 8 plus 7 plus 2, and here the 19 is equivalent to 6 plus 4 plus 9. So we now get the mean. So the average now is the square of the standard deviation. That is, the deviation of each of them from their mean is equivalent to the variance, and after that we now square it. So here you can now see that each of them here is, we now do 3 minus the mean here is 3.894. So we now do 3 minus 3.894, 4 minus 3.894, and 5 minus 3.894. The same to here. We also do 0 minus 0.6. So 1 minus the mean, 2 minus the mean. So when we are done, we multiply them by the frequencies also. So once we are done, we are able to get their variances. Now there's what we call the within class variance and the between class variance. I will explain that later, but each of them has a formula. Now this is the formula for the within class variance here. So what the formula now is that you are going to multiply each of their weights by their variance and add them and sum them together. You get what we call the within class variance. Now if you do this, now what we got is the within class variance using 3 as the threshold. Now when we are done, that is assuming we use different values at the threshold, this is what we are going to, this table is what we are going to get. So this is what we did for this one using 3 as the threshold. So here you can see using 0 as the threshold, using 1 as the threshold, using 2 as the threshold, using 4, and using 5. So their calculation, these are all the stuffs you will get. These are their weight, their mean of the background, that is the black side, the variance of the background, the weight of the foreground, mean of the foreground, the variance of the foreground, and then finally the within class variance using the formula we saw in the previous slide. So from Otsu's law or Otsu's formula, Otsu states that the right or the best threshold is a threshold in which the within class variance is minimum. So you can see here that at the threshold t is equal to 3, that the within class variance is 0.4909, which is the smallest compared to the rest of them. So Otsu states that at this point, that particular value is the best threshold. So and you can see from the pictures we get from there that this particular picture here seems to have a better distribution of white and black within it. So this is what the usual calculation we expected to calculate each of the threshold, to calculate the within variance of each threshold. At the end of the calculation, we now check the one which has the smallest within class variance. So now it's going to be tedious, especially when the thresholds vary from 0 to 255. Remember, this is just an example. In a real picture, at times the values can reach 255 or more. So that is why a more easier solution was invented, which is referred to as the between class variance. So the between class variance this is the formula for the between class variance here. Now, if you calculate the between class variance and place it side by side with the within class variance, now a new law is stated that the best threshold is a threshold where the between class variance is maximum, and where the between class variance is maximum is equivalent to where the within class variance is minimum. So in our calculation, I will show you how the between class variance is being calculated. So the between class variance is easier to calculate compared to within class variance. So we are going to drop the within class variance. So we won't be using the within class variance in our implementation. Rather, we'll be calculating the between class variance because it's easier and faster. I'll show you the calculation later. Now, with this picture, we are going to differentiate between the within class variance and the between class variance. So assume this to be an histogram distribution of pixels, and the center here is the threshold. Now remember that the variance is the degree of scatter or the distance of each of the points from their mean. Now within each of the colors, now within the black region there is a mean, and within the white region there is also a mean. Now the variance, which is the distance of each of the points from their mean, that is the distance of each of the points of the black part from their central mean, is the within class variance, and also the distance of the white region from the central mean here is likewise the within class variance. Now the between class variance is now the distance of all of them from the central threshold, that is the center here, is now called the between class variance. So remember, the within class variance has to be very, very small. Yes, it has to be very, very little. So if the within class variance is small, it means that there are each of them, the white part and the black part, they are all centered very close to their mean, which is very good. So it means that the within class variance were spotted well. So if they are well centered around the mean, that means the variance will be small. So it means that that particular threshold is good. But for the between class variance, the wider the variance, that is the more distance they have from the threshold, the better. So that is why for the within class variance, it has to be very small, but for the between class variance, it has to be big. So what it means by being big is that the threshold, which is this one at the center, has to be far from both of them very well. So the threshold shouldn't be towards the black part and it shouldn't be towards the white part. It should be at a point where it's equally distanced and well differentiated from each of the white and the black parts. So you can still ask me more questions or you read it up more if you don't understand my explanation. But I'll simply go to the calculation of the between class variance. Already we have done the calculation for within class variance earlier before now. So we simply do calculation for the between class variance and then we go straight to the code. So now the formula to calculate the between variance is given here. So this is a formula we are going to calculate in this course. So WB times WF from our previous calculation is 0.4722 multiplied by 0.5278. Then you have your MB minus MP minus your UB minus UF. So here is 0.6471 minus 0.8947. So since it's squared, the negative value doesn't mean anything. So we are just trying to find the difference between the two mean. So the difference between their mean, which is 0.8947 and 0.6471. So if we get the difference, we square it and multiply it by their weight, we will now get 2.6287. So remember here is equivalent to the answer that was gotten here. So this is what we are going to calculate in this course. So, and this aligns with the graph I showed you earlier. This graph, I told you that the between class variance is the mean of each of them, the variance between the mean, the distance between the two mean is what is called the between class variance. So with this simple explanation, I think we are good to go into the coding section of this course. Thank you, and meet you in our next class. So the advantage of calculating the between class variance instead of the within class variance, as you can see here now, is that to calculate the between class variance, you no longer need to calculate the variance, this particular part. But if you are calculating the between class, the within class variance, you need to calculate the variance. But for between class variance, it's no longer needed. So that is why we prefer in our application to calculate the between class variance instead of the within class variance. So let's begin. So in this lesson, we are going to start calculating the Otsu Binarization. So to do it, you just simply call the function Otsu Binarize and pass an image to it. Remember I told you that you are going to see the application. By the time we start discussing the logic and the logic XOR, logic Nand, we'll be implementing the Otsu Binarization, because you know that logic gates, the AND gate, the OR gate, they all operate on binary values. You know, you all ones and zeros, or you all high and low. So that is why we need to binarize the image into only two parts, white and black, so that we can be able to apply logic operations to it. These logic operations are they are very tremendous effort in image digital processing. So what have we done on line 73? We declared the Otsu Binarize function. So the first thing we are going to calculate is the image histogram. So what this histogram does is it calculates the frequency of each color pixel. Now we created an empty array called histogram, size 255 on line 74. So what this array does, that we are going to use it to accumulate the image pixel on line 76. So we use 255 because we will be applying binarization on grayscale images, not colored images. And you know, grayscale images, the range of color ranges from 0 to 255. So we are going to calculate the intensity, that is the frequency of each color within the image. So on line 77, whenever we see a pixel color, maybe we see color 20 or color 100, we increment it. We'll be doing the incrementing on line 82. The for loop on line 76 is just used to initialize the array. So you can see that on line 77 we set everything to 0 from I0 to I255. So on line 82 is when we do the actual incrementing. So we keep record of our so what we are calculating on line 82 is just the frequency of each pixel. Remember, we calculated that in our calculation when we drew the histogram. The frequency was used to plot the histogram. So that is what we are calculating on line 82. So on line 79 and 80, we are going to loop throughout the whole image pixel. Whenever we get a pixel color on line 81, we read each pixel color and then we increment it on line 82. So we are keeping the count or the frequency of each color pixel. So on line 81, assuming with the pixel we got is 20, that means on line 82 we increment histogram 20. If we read pixel 255 on line 81, on line 82 we increment histogram at index 255. So each image color or each pixel value has its index on line 82, which we increment. So 82, the histogram array stores the frequency of each color pixel. Then on line 85, the for loop calculates the total weight of all of them. So what we are doing on line 86 is each of the frequencies we get, we multiply it by the color. So assuming frequency color 25 appeared 5 times. What we are doing on line 86, we multiply 25 by 5, we add it to the sum. If color 10 appeared 2 times, we do 10 times to 20, we add it to sum. So we accumulate the total weight of all of them. So the weight is equivalent to the color multiplied by the frequency on which it occurred. And now on line 85, we are only looping to 255 since it's a grayscale. And you know, grayscale images range from, is an 8-bit pixel. So it ranges from 0 to 255. And we're also applying it only to grayscale images, because it's easier to apply to grayscale image than to colored images. So next, on line 88, 89, 90, 91, 92, we are declaring some variables we are going to use. So our threshold will be stored on the threshold we created on line 92. So we have the background sum on line 88. Then we have the weight of the background on line 89 and the weight of the foreground on line 90. So we've done this already before. So on line 91, we store the maximum between class variance on line 91, and that is what is going to finally become our threshold on line 92. Now on line 94, what we are doing is that this for loop on line 94, we are going to use this for loop to calculate the between class variance of all of the image colors. So here, what we are doing on line 94, we loop from 0 to 255. So from 0 to 255, we are setting all of them to the threshold. So when t is equal to 0, that means we are using 0 as the threshold. We calculate the between class variance using threshold equal to 0. We calculate between class variance using threshold equal to 1. We calculate the between class variance using threshold equal to 2 until 255. So we are going to calculate the between variance using the threshold t equal to 0 up to t equal to 255. Then once we are calculating it, We are comparing to know which of them has the maximum within class variance. Anyone that has the maximum within class variance, we store the between class variance as the var max on line 91, which is this var max we created on line 91. So at the end of the loop, the var max, which is the final one that came out as the highest between class variance, we are going to set it to our threshold on line 92. So next, within the loop on line 95, we calculate the background weight. So example, if we set when t is equal to 0, that means 0 is background, from 1 to 255 is the foreground. If t is equal to 10, that is the t within the for loop on line 94. Assuming is equal to 10, that means from 0 to 10, we are going to use 0 to 10 as a background, and then we use 11 to 255 as the foreground. If when t is equal to 100, it means 0 to 100 is the background, and 101 to 255 is the foreground. So that is what we are doing. So on line 95, we accumulate all the histogram values on line 95. We are going to accumulate them up to where t is. So when t is equal to 0, WB will include histogram t equal to 0, histogram t1 is 1, t2, t3, t4 up to t10. So 95, WB is an accumulator, accumulating the frequencies. So in our last calculation, we called WB the weight of the background. Now, if the WB is 0, that is, we've not accumulated anything, or probably the frequencies have been 0, we call continue. It means that such WB cannot be used as the threshold. The T cannot be used as the threshold. So we increment it again. If the WB histogram is still 0, we go to another loop, we increment it again. So it means that such T cannot be used as the threshold. Then, on line 98, WF is the foreground weight. Now, the total number of pieces we have is equivalent to im rows times im cols. If you multiply im rows and im cols, you get the total number of pieces we have. Now, when you subtract the background weight from it, the rest of what you get is the foreground weight. The background weight plus the foreground weight will give you the total number of pixels. So that is what we did on line 98. We subtract WB from the total number of pixels, we get WF. And we keep subtracting. Whenever WF equals 0, it means we are done. We break from the loop. Now on line 101, we calculate sum B. Sum B is each of the histogram multiplied by t. So we are going to use sum B to calculate the mean. Sum B means the background sum. So you are summing each of the frequencies times their value, and you are accumulating it in sum B. See, we are using plus equal to. Then on line 102, we are calculating the background mean. The mean of the background is equivalent to sum B divided by the weight of B. So sum B is the total histogram multiplied by the value of t, and we are accumulating it. And once we divide it by their weight, we get the mean of B. Then on line 103, sorry. Oh, I've skipped an important part. So whenever we get back, I'll continue explaining. At this point, we've calculated T, which is the threshold. So what we are going to do now on line 73 is that we are going to pass the threshold as an argument to this threshold function on line 73. So now we've gotten the threshold. We now pass it as an argument on line 73. So what we are doing on line 73 is that we are now going to set all pixel value below the threshold to 0 and all pixel value above the threshold value to 1. So that is what we are going to do now in this threshold function. Now, but remember, we are going to create a new image before doing this. We won't use our original image. So you can see what I've done here. We loop throughout the image pixel on line 76 and 77. We get the pixel, store it on line 78 into the pixel variable. Then we now check on line 79. If the pixel we get is greater than or equal to the threshold, we assign 255 to it, else we assign it to 0. So now we are going to test it. So we now have only two colors, 0 and 255. So we will still change it to 0 and 1. Now we are doing a test. So you can see this is the grayscale image and this is the binarized image. So you can see we have only two colors here, white and black. So Otsu Binarization is very important. We are going to use it in logic operation. So on line 79, so we are setting the pixel value on line 80 to either 0 or 255. So that is the only two colors we are going to take. Now back to our threshold. So back to our threshold, we were on line 116 before we moved. So here the sum B is accumulating all the histogram from 0 to our current t multiplied by t. Now the mean is sum B divided by the weight of B, and then MF is now the sum minus sum B divided by WF. Remember that the sum on line 118 is the total sum of all of the histogram t multiplied by t. We did it in the up, we just skipped it already. So if you must subtract sum from sum B, you are going to get, maybe you call it sum F. So you divide it by WF, you get the mean of the background. So on line 120, we apply our formula on line 120, the formula we used, and then on line 122, we compare our var between class variance, which is also called var between on line 122, with the previous var max. So if it's greater, we set the var max to the var between, and then we call that threshold t. The t at that point is what we are looking for, not the var max or the var between. So the threshold t is what we are looking for. So on line 122, we just print the threshold, and on line 128, we call the threshold value. So the threshold value is going to do the division, dividing the colors into two equal parts. Please send your questions if you do not understand this, and I'll see you in our next class. Thank you. Welcome. So in this lesson, we are going to learn the applications of Otsu Binarization and thresholding. Already, we've seen that Otsu Binarization is used in thresholding. So you can see that when we call the threshold function, the new image was divided into 0 and the 255. Already 0 means zeros, 255 in binary form means 1. So for operation on line 132 logic AND, 137 logic NAND, 138 logic OR, 139 logic XOR, and that addition and subtraction. These 6 operations will only use binarized images because they are binary operations and they operate only on zeros and 1. So 0 and the 255, you know that 255 is 1 8 times and 0 is 0 8 times. So that is what we've done. We've binarized the image, converted it into 0 and 1, and it's time to apply logic operations to it. So our first logic operation is logic AND on 132. So what we are checking on 133 is that we are trying to make sure that the 2 images are of the same size, height, and width. So this logic operation, what they are doing is that they are merging the 2 pictures together using, you are going to see what the output of these images will be. So, but for you to merge the 2 images together, we have to make sure that they are of the same height and width. Because if not, when you want to add a particular pixel that is not existing, a particular length that is not existing in one of the pictures, is going to throw an error. So on line 133, we are simply checking to know if the 2 images are of the same size. So it's very important to make sure that the images are of the same size. If not, we exit. So on line 138, we are creating 2 new images on 138. So what these images are doing is that we are going to binarize our old image. So now on line 132, when we pass the 2 images, im1 and im2, on line 138, we binarize the 2 of them, on line 138 and 39, into 2 new images called new im1 and new im2, on line 138 and 139. So these 2 new images created here are now binarized. We've called the binarization on them. So they are now binarized. So after applying the logic operation, we are going to place them inside a new image called new image on line 140. So as usual, 141 we start looping. So on line 141 and 143 are the 2 for loops that we loop through the binarized images. So it's just looping one of them, but they are assumed to be the same size. So on line 145 is applying the logic operation on the 2 images at those points on line 145. So you can see the double AND since we are applying the AND operation. So it's applied this AND operation on them on line 145. So after applying it, so you know when you AND a series of 1s, you can get 1 or 0. So on line 146, it checks the output, whether it's equivalent to 0 or 1. So if it's equivalent to 0, we set it back to 255, else we set it to 0. So the reason about this, remember that if the pixel is 1, it does not mean black. If it's 0, it means dark black. If it's 1, it still means black. So, but there is no representation for white here. So, anytime is equivalent to 1, you set it to 255. So, on line 154, for logic NAND, we copy exactly the same thing as the logic AND and paste it there. But the difference is that on line 167, we are going to implement the NAND operation. That is the inverting operator on line 167. So back on line 172, 173, and 174, we display the two images and then the final output on line 174. So on line 167, you can see how the NAND was applied to an AND operation. Now for the logic OR operation, we do exactly the same thing. We copy the same code. On line 189, we are now going to change the AND operation to an OR operation. So, but every other thing remains the same. Just the operation we are changing. So we do this for almost all of them. On line 198, for the logic XOR, we are still doing exactly the same thing. So for the logic XOR, this is how it's being implemented. So we AND the two images while noting one of them, and then we OR it with the AND of the image again while noting the other image. So if you write this out on the paper, it's going to make sense. That is a way of representing a XOR operation. Then for addition, on line 234, we simply change the operation to addition. So we plus the two image pixels together. So you know, when we are adding the two pixels, assuming the both pixels are 255, 255, there are tendencies that they will exceed the range. So on line 235, we just check and make sure it doesn't exceed the range by simply picking the minimum. If it's above 255, we pick 255 as the pixel and ignore the rest. So for subtraction, we perform the same thing. We simply subtract the picture on line 256. So subtraction on line 256, we are using minus to subtract the two images here. So hopefully in our next class, we are going to test all of them. So you are going to see the effect of what the logic operation and how Otsu Binarization was used to achieve this. in our next lesson. Thank you and see you in our next class. Welcome. So here we are going to test our logical operation. So the first one, you've seen it, is the logic and. So this is the syntax in the command line. So we give the location of the first picture and the second picture. So when I test it, this is the first picture here. Then this is the first picture. This is the binarized image here. After it has been binarized into black and white, this is the second picture. This is what it looks. You can see this binarization came out very well because the threshold was picked. The threshold was perfect. Now, this is at the grayscale, and now this is the logic and what it looks like. So you can see how it placed the second picture on top of the first one. So it's a way of adding two images together, merging them together. Now we are still going to implement the colored one. So next, let's try the logic Nand. So for the Nand operation, this is the images. This is what the Nand looks like. So by the time we are still going to apply it to the colored image, it's going to look much better. So the Nand also merges them together, but in a white color. So and merge them together in a black color, while this one merges them together in a white color. So next, the OR. So this is what the OR does. It removes the first picture from the non-colored one. Then we'll also try the XOR, the addition, and finally the subtraction. So watch closely and see each of the functions we are applying. This is the XOR. So the XOR keeps one of them in a black background and the other one in a white, using a white pixels. Welcome. In this lesson, we are going to discuss another technique. But before that, let's learn how to calculate contrast. Contrast is used to raise the brightness of an image. So it's calculated as the maximum pixel value minus the minimum pixel value. So here on line 268 and 269, I have created two functions used to calculate the minimum pixel value and the maximum pixel value. So I will describe those two functions now. But on line 271, the contrast is equal to the maximum pixel value minus the minimum pixel value the image has. If it has white, then the maximum will be 255. If it has pure black, the minimum will be 0. So if you do 255 minus 0, that means the contrast is equivalent to 255. So this is the maximum pixel value here. So on line 133 and 135, we are just looping through the rows and column, and we are just checking on line 135, the new 135 now, we just check the maximum value pixel. So we use the max function to do that. So all we do is to check between the current pixel and the previous maximum pixel, which one is greater. So we return the maximum pixel. So the same is done for the minimum pixel on line 140. So we use the two for loop on line 145 and 146, 145 and 145. So we are trying to get the smallest pixel value. So once we get the maximum and the smallest, the difference between the two of them is the contrast. So you are going to see how we apply the contrast to improve the brightness or color of an image. The luminance. Here, the luminance is the average pixel value. So to get the luminance, we just sum the sum total of pixels we have. Then we divide it by the total number of pixels. So on line 309, we are accumulating the total pixel values that we have. So once we are done summing them, we divide it by the total number. Next is the linear contrast. Now in the linear contrast, we are going to implement the contrast we just found earlier. So the formula for calculating the linear contrast is given on line 303. Now, instead of doing the max minus min, we just put the contrast there. So remember that the contrast is equivalent to the maximum pixel value minus the minimum pixel value. So now we replace this with the contrast. So we calculate the contrast of the image. So when we implement this linear contrast, we are going to see the change between a picture that does not have linear contrast and after the implementation. So the linear contrast improves the brightness of an image, and the formula is given on line 303. Is equivalent to 255 times the pixel minus the minimum pixel value divided by the contrast. Now we use 255 because it's the maximum value of the pixel. Since each pixel is 8 bits, that means we are going to use 255. So whatever pixel you get, you subtract the minimum pixel value from it, multiply it by 255 or the maximum pixel value you can get. then you divide it by the contrast. It's going to tremendously improve the contrast of the image. So when we go to testing, you are going to see the implementation and how it works. Now, on line 393, we have the linear contrast saturation. This is equivalent to the contrast, but the difference is that instead of when we were doing the linear contrast, we simply used the contrast we calculated. And you know that the contrast is equivalent to the max minus the minimum pixel value. But here on line 293, we are introducing a max and a min on the arguments. Now we are not going to use the original max and min of the original picture. So to do the linear contrast, linear contrast saturation, we are trying to saturate the image with an artificial minimum and maximum. So on line 406, you can see that we did the x max minus s min on line 406 instead of dividing by the contrast, because the max and the min are generated values. But on line 294, we are going to make sure that the mean we are using is not less than the original mean of the pictures, and the max we are using is not greater than the original max of the image. So we are trying to saturate the image within a given range. So is equivalent to the linear contrast we calculated, but is using its own max and min rather than the max and min of the image. Then finally, histogram equalization. So histogram equalization is another image improvement technique to use. So the formula is best described on a graph, but it's very easy to understand by reading the calculation. So on line 319, we calculate the image histogram, just like we did when we were doing Otsu Binarization. So on line 319 or 319, so we increment each pixel whenever we meet a pixel on line 318. We go to the index and increment it. So we are just counting the frequency of that pixel. So next we calculate the cumulative, the CDF, and then they have the CDF mean. So you can see the formula here on 326 and then 327. So the histogram equalization is a very important technique in image processing, and this is the actual formula for calculating it. When you go online, people do the calculation using different kinds of formulas. Some are wrong, but here this is the original formula for calculating it. When you apply it to an image, you are going to see the effect on the image. So on line 334, we are just simply displaying the chart. So it comes like a chart where first you calculate the histogram, then the CDF, the SK, the CDF mean, and so on. So with this, by the time we get to the testing, when we are going to test it, we are going to see the effect of each and every technique we discussed in this class. But it's quite noteworthy to note the formula and how they are being implemented. So in our next class, we are going to test it. Welcome. So in this lesson, we are going to learn another 3 techniques: brightness, scaling, and field filtering. So how do we brighten an image? So remember that an image pixel ranges from 0 to 255 because each pixel consists of 8 bits. So from 0 is black up to 255. 255 is pure white. So while the pixel ranges, as the pixel value increases, it changes from black to white. So by generally increasing the value of every pixel, you are equally increasing the brightness of that image from dark to light. So to increase the brightness, all we have to do is to simply increase the value of each of the pixels by a particular number. Here we refer to that number as level, and is part of the brightness argument on line 431. You can see level. So level can be a value as small as 5 or as big as 50 or so. So depending on the intensity you want to increase the brightness to. So here on line 434, 435, we've given the for loop that will loop throughout our pixel for us. So on line 436, we are going to grab the pixel, the original pixel, add the level value to it, and set it to the pixel of the new image. So remember, we've created a new image on line 432. So this new image on line 432 will be the image that will contain the new brightened image. So whenever we do get pixel on line 436, we get the old pixel, add the level to it, and set it to the pixel of the new image. So you can see how we get the pixel and how we added the level to it. And then we use the mean function on line 436. The mean makes sure that the value we get after incrementing the pixel with level does not exceed 255. Remember, 255 is the max. So here we choose the minimum between 255 and the pixel we get. If the pixel is exceed 255, we pick 255. If it's less than 255, we pick the value. So then we also have the max function. So the max makes sure that it's not below 0. So in case you are trying to dim the image, you are going to use a negative level value. So if you subtract the level from the pixel, it might go below 0 depending on the initial value of the pixel. So we use the max function here to make sure that if it goes below 0 and we choose the max is going to select 0 for us instead of a negative value. And finally, we set the pixel value to it. And then on line 439 and 440, we display the image, the old image and the new brightened image. So next, on line 464, scaling. So how do we scale an image? So, we can scale just the width or the height or both of them. So you can decide to increment only the width, or you can decide to increment only the height, and so on. So whatever multiplier we are using to increment, whether a value less than 0, which means we are trying to reduce the size, or a value greater than 0, that means we are trying to increment the size. So whatever value it is, we are going to pass it as the argument as x scale and y scale on line 464. So 465 and 466, we use the multiplier to multiply the old rows and columns of the old image. So if maybe we want to increment the width by 2, that means x scale will be equivalent to 2. So if we multiply in codes by 2, we get a destination width dstw on line 465. So that means it's now going to store the value of the old column multiplied by 2, and the same for 466. If we want to decrement the size, we can use a value below 0. Multiplying a value below 0 reduces the original size. So assuming you want to reduce the size by half, we can multiply it by 0.5. Then we now create a new image on line 468. This new image will now have the new column and the new width, which is equivalent to destination W and destination H. On line 468, we create the new image using the new sizes. In case you want to increment probably only the column, you can set the Y scale to 1 and not 0. Setting the X scale or Y scale to 0 means you will get an error. That means you are trying to set the height or width to 0. So it's not possible. So if you don't want to change either of them, you set it to 1. So after creating the new image on line 468, now within our loop, so what we are going to do is, we are now going to set the pixel of the resized image to the pixel from the old image divided by the Y scale and the X scale. So when we do the practical, you are going to see that everything came out well. So by dividing on line 471 with Y scale and X scale, you get the new pixel location for the new image. So finally, 474 and 475, we display the gray image. So we do it for the colored image. On line 471, 472, 473, we are now using set pixel value 3. That is, you want to implement it on the colored image, not just the grayscale. But you can likewise decide to implement on a grayscale. So next, let's talk about filtering. On line 442. Now, how do we filter image? Just like when you are using your Instagram and you are getting different shades of filter. Filter is very simple. By varying the degree of concentration of either of the colors, red, green, or blue, you get a filtered image. Yes. By either increasing the intensity or decreasing the intensity of one or more or a combination of the red, green, and blue color concentration in an image, you get a filtered image. So now we have the multipliers as arguments on line 442. We have the multiplier R, G, and B. So these three multipliers, the R will be used for the red, green, G will be used for green, and B will be used for blue. So depending on the intensity, you want to alter the concentration of the color. So probably, maybe if you don't want to alter all of them, you set the particular one to 1. So it doesn't get altered. On line 447, we simply get the old pixel and multiply it by the multiplier. Already we created the new image on line 443. So like on line 477, for the red, which is 0, we multiply it by R. So in case you don't want to alter the red color, you set the R to 1. That means here, if you multiply it with 1, you still get the old value. So here you can see that that is how we repeat it for the green and the blue. So we simply alter the concentration of the color and we produce a filtered image at the output. So on 452 and 453, we display the old and the new image. So you see the effect of the filter. And then finally, in our next class, we are going to test these three functions. These techniques we implemented: the brightness, scaling, and filtering. So thank you and see you in our next class. Welcome. So in this lesson, we start talking about convolution. Now, convolution is a very important image processing technique. Already we've discussed histogram. We used histogram when we were talking about Otsu Binarization, and we also use it in histogram equalization. And we can as well use it in increasing the brightness of an image, and so on and so forth. So, but in this lesson, we are going to discuss convolution. It's a very important aspect of image processing. Now, without going much into the theoretical aspect, we just simply discuss the most practical aspect of it, of convolution, so you'll be able to understand what we are going to be treating in this lesson. So in convolution, you are multiplying or you are sliding a mask through an image pixel. So a mask is also a matrix of odd numbers, usually like 3 by 3, 7 by 7, 5 by 5. So let's start with an example and show you what a convolution looks like in application. So consider this to be an image, the image matrix, and this is the mask that we want to slide over the image. So as usual, we're going to slide this mask through every pixel within this image. We'll slide it through 2, 4, 6, 8, 10, 12, 14, 16, and 18. So in our code, we are going to have our 2 for loop. We are going to loop through all the pixels of the image. Now, while sliding it, we are going to keep the center of the mask on every pixel. So assuming we want to slide it on 2, we are going to keep 5 on it. So let me show you how they are going to be. So when we slide it, we get this. And the first slide, the first number in our image matrix is 2. So we get the center of the mask, which is 5, slide it on top of 2, and then you can see how we place others. Now, the column 9, 6, 3 and the row 9, 8, and 7 did not overlap any part of our image matrix, so it's going to be discarded. So only the ones that overlap is what we are going to use. So here you will now see that we have 2 multiplied by 5 plus 4 multiplied by 8 plus 8 multiplied by 2 plus 10 multiplied by 1 is equivalent to 52. So we now use the new image pixel. We now have 52 stored in place of 2. So this is how we do convolution. So after sliding the 5 on top of 2, we slide 5 on top of 4, then we slide it on top of 6, then we slide it on top of 8, then we slide it on top of 10, 12, 14, 16, and 18. So while we are doing it, any of the values that do not overlap with any image pixel, we discard it. So I'll show you the technique we use to check if a pixel will overlap or not. So in our code, while we are using our for loop to loop through each of the pixels of the image, whenever we get to a pixel, we are also going to loop throughout the mask. So just like we used to have 2 for loops, we are going to have 2 for loops and then another 2 for loops. That 2 for loops, the new 2 for loops will be looping through the mask, doing this multiplication, and it will also be checking if a particular part of the mask does not overlap. If it does not overlap, we discard it. So you see the implementation in our code. So next, when we slide the center of the matrix of the mask 5 on 4, we get this, and then when we slide it on 6, we get this. So we use the same method to do the multiplication and the summation. But while we are doing it, remember anyone that any part of the mask that do not overlap is being discarded. We only sum the parts that got overlapped. So the most critical important part here is knowing which particular part overlaps and which does not overlap. So next, let us check how to test for overlapping. Now we are going to consider these 1, 2, and 3 masking. So in the first one, our center mask, which is 5 is the center of our image mask. You can see is overlapped on 2. Then in our second convolution, 5 is overlapping in 6, and then in this other convolution, 5 is overlapping on 18. Now, in our code, we are going to see this particular line of code. So the first for loop loops through the rows and column of our image, while the next 2 for loops, which is looping through case size using M and N, is looping through the image matrix. So the image matrix is in red, our main image is in black. So we are going to use these 4 formulas to check for overlapping. Now, in our first matrix we want to test, let us test for the upper row, which is here is 987. So let us prove that 987 does not overlap. So to prove that, we use this formula here, I plus M minus K center is less than 0. If I plus M minus K center is less than 0, that means it does not overlap. So what we do is we break out of the loop and we break out of the loop that loops through the image matrix, not the whole for loop. So only this last loop that loops through the image matrix that we're going to break out of. So we use I plus M minus K center is less than 0 to check if the upper part of the image matrix overlap. Now the K center is equivalent to the center of our image matrix, and is equivalent to the image mask divided by 2. Now our image mask here is 3 by 3 matrix. So if we do 3 divided by 2, you get 1. We are discarding the decimal since we are working with int. So here, if the mask is a 3 by 3 matrix, that means 3 divided by 2, the K center is equal to 1. If the mask is a 5 by 5 matrix, we do 5 divided by 2, you get 2. Therefore, the K center is 2. If the mask is a 7 by 7 matrix, we do 7 divided by 2, you get 3. Therefore, the K center is equivalent to 3. Now, for the first matrix we want to test, we check where the center of the mask overlap. Now, the center of the mask is overlapping in 2, and the position of 2, the I and J of 2 is 0, 0. 2 is in row 0, column 0 of the image matrix. So we are not considering both the mask, we are just considering the position of the center of the mask, which is 5, is on 2, and 2 is position 0, 0. So to check for the upper row, we get the row of 2. The row of 2 is 0. We won't be considering the column here, since we are checking for if the upper row overlap. So remember, we want to check if 987 overlap. So since 2 is in row 0, therefore in our formula here, I is 0. Now we check for M. M is the particular row we want to test. Now 987 is row 0, so M is 0. So we now do 0 plus 0 minus K center, which is 1. You get minus 1. 0 plus 0 minus 1, you get minus 1. So minus 1 is less than 0. Therefore, 987 does not overlap. We break out of the loop. Okay, if that one is hard enough, let us try another one. Let us check if this first column overlap 986. So we use this formula here, J plus N minus K center. Now we already know that K center is equal to 1. Now J plus N. Now N is the column we want to test. We are testing for column 0 of the mask. Now J is the column where the center of the mask overlap is still 2. So, and 2 is in column 0. So they are both 0 and 0. J and N is 0 and 0. So you do 0 plus 0 minus K center, which is 1. You get minus 1 again. Therefore, this leftmost column, 9, 6, and 3 does not overlap. We continue. That is, we go to the next loop. Now let's check for the rightmost column, 741. So the same way we test for 987 here, that's how we test for 987 here also. You find that it's still the same thing. It doesn't overlap. But here, 5, which is the center of the mask, is overlapping on 6. But the values are still the same because 6 is still on row 0. If you take 5 and place on 2, 2 is still on row 0. So 987 will still show you that it does not overlap. Now let's test for 741, which is the rightmost column. So to test for the rightmost column, 741, we use this formula here, J plus N minus K center, if it's greater than im cos. Now we already know that K center is equal to 1. Then im cos is the total number of columns we have. Here the total number of columns we have is 4. No, it's 3 columns. In the image matrix, the total number of columns is 3 and the total number of rows are 3 also. Now, im cos is 3, im rows is also 3, and our K center is 1. Now to test for 74, we check 74, which column is it within the mask? Is in column 2. This is column 0, column 1, and column 2. So N will be equal to 2. Now, where does 5 overlap, which is the center of the mass? It's overlapping on 6. And 6 is in what column? 6 is in column 2 also. Here is column 0, column 1, and column 2. So J here is 2 also. So when you do 2 plus 2 minus K center, which is 1, you get 2 plus 2, 4 minus 1, 3. Is 3 greater than or equal to im cos? Yes, 3 is equal to im cos. Im cos is also 3, so 3 is equivalent to 3. We continue. It means that 7, 4, and 1 does not overlap. Now let us check for the bottommost row, 3, 2, 1. So here, 5, which is the center of the mask, is overlapping on 18. And 18 is in column 2, row 2. But since we are checking for the row, we just take the row of 18. 18 is in row 2. So here, I is equivalent to 2. Now, M, which is the row we want to test, 3, 2, 1 is the row we want to test. So 3, 2, 1 is in row 2 also. This one is row 1, row 2, no, row 0, row 1, and row 2. So M is also equivalent to 2. So if you do 2 plus 2 minus K center, which is 1, you get 3. And 3 is also equal to im rows. So we break out of this loop. So this is a simple way we are going to be testing if a particular part of the mask overlap or not. And that is the major heck of this convolution. And we've been able to explain it. So let's say we want to test another one. So there are some parts where they are mixed. Example, in this last matrix. So assume we want to test if 9, 8, and 7 overlap. You find out that 9 and 8 overlap, but 7 does not overlap. So in this case, all the rows overlap, 9, 8, 7, but the column 7 is part of 741, which does not overlap. So by the time you do this calculation here again, you find out that 7 will not be included. So we either break or continue in it. So without wasting much time, let's go to the implementation in our course. So now, let us go to the implementation of convolution to our course. So line 369, the convolution function takes as image 1, the image we want to apply convolution on, 2, the kernel or the mask. Now, most of the kernels are 3x3 matrices. So here you can call it kernel or mask. Then 2, the k size, which is the size of the kernel. Here, the kernel, the size is 3. And then norm. Norm is just an identifier that you can use to multiply the whole matrix after the convolution. So the new image where our convolution process will take place on is created on line 370. So remember how I told you we calculate k center. That is what we are doing on line 371. So we simply do the size of the mask divided by 2. So on line 374, we'll be implementing the 4 for loops we discussed in our last class. Now we've drawn the 4 for loops, and now we are checking if they overlap. So as usual, the first 2 loops through our image matrix, while the next 2 for loops through the matrix, loops through the mask. So on line 388, now 83, sorry, we've been able to check the overlapping already on line 378 to 382. Now on 383, we are now going to do the summation, accumulate the sum. So within the loop, we keep multiplying the overlaps, the places where the mask overlap with the image, we keep multiplying them and accumulating them within the sum. You can see where we multiply with the kernel, m by m, and then we multiply it with our image, where we did image get pixel. So we added the location of the image pixel. So the location of the image pixel is equivalent to I plus m minus the k center. So when we are done on line 386, assuming that usually the norm is equal to 1, but if there is a norm is just used to divide whatever sum or multiply whatever sum you get. So once we are done, on line 388, we now set the new image to the pixel. When we are done on 389, we reset the sum and start the loop afresh. Now they have a 2D convolution or second order convolution. So they have the theoretical derivation, but in practice is nothing other than the difference between the 2D convolution is that you flip the mask horizontally and vertically, and then you still apply the normal convolution to it. So what we are going to do in our case here in the 2D convolution is that we are going to simply flip the mask in the function called convol2d on line 395. So that is the only thing it's going to do. After flipping the mask, it's still going to call our initial convolution function. Now we pick the kernel is in the argument. We call it kernel, which is our mask. Now we create a new mask called kern on line 395. So this new mask called kern will now store the transformed kernel after rotating it horizontal and vertical. So now use this new kernel called kernel 295 and then use it for the convolution instead of the original kernel passed as argument on 294. So you can still line 401, we are calling the convolution after the transformation. So line 298, we are transforming the old kernel and setting it to the new kernel called the kern. So in our next class, we will use it to implement all the filters and test them. So thank you and see you in our next class. So in our last class, we learned about convolution and 2D convolution. So here we are now going to learn how to implement it. So for our filters, Gauss filter, smoothing filter, sharpen filter, edge detect, Robert filter, Prewitt filter, Sobel filter, evaporation, convo, and erosion. All these techniques implement convolution in them. So what we are simply going to do is that, but the difference between all of them is that they have their own unique mask, but they still implement exactly convolution in them. Now they have a derivation, the theoretical derivation, but in our practical sense, that is, the theoretical derivation was used to derive their mask. So in this lesson, we are just going to name include all their mask within their function. So in our next class, we test them. So you see the outcome of applying each of the masks on the image using convolution. So the difference with all of them is that they all have a unique mask, but they apply convolution on them. So watch carefully. They have, so you don't need to cram all of them. You can just get the matrix whenever you want to apply any of them. So we'll do the implementation in our next class. So you see how the edges of a picture are being detected, how a picture is sharpened, how the smoothing filter and Prewitt filter applies blur to an image. Gauss filter applies blur to an image. So you have erosion. The erosion is used to erode the edges of an image. So, and so many more. So, but these ones are the major one that have very common mask, and we'll test them in our next class.